Thank you for the opportunity to participate in this fantastic training experience. I will start sharing my screen now. There it goes. I hope you see it. So indeed, we're going to talk about VLBI networks. I know there has been a lot of context already about what is interferometry, what are some of the exciting science that can be done. Now, to have, here we go, to have a good view of what are the different instruments that exist around the world and what are their characteristics. I have prepared this talk in which I will first give a very brief introduction and a bit of the history of VLBI, which just a few years ago was the 50th anniversary. So it's not like a very young thing. It's a very mature technique in radio astronomy. Then what are the main networks for VLBI at centimeter wavelengths? And you see that there are not a few, there is a number of them. Also, which are the networks at other frequencies and even at other usages that are not only astronomy, other kinds of networks. And finally, my pledge, as Melvin says, that well, there is this opportunity to work towards a global alliance of VLBI networks. So that I hope that I can cover that in around an hour. Let's see, and then we have some time to chat. So the whole thing about VLBI and the whole thing about interferometry is the quest for very high angular resolution. It has been possibly already explained that if you have a single antenna, in this cartoon, I chose a parabolic antenna. You can point it to some area of the sky, and then you are sensitive to the a fraction, a very tiny fraction of that sky that is kind of a circle around the position in the sky where the antenna axis is pointing, and the size of that circle depends on both the diameter of the antenna and the frequency of operation. So
sorry, Paco,
yeah.
can you enlarge your screen a bit or put it in a full view mode? Full screen mode.
It is already in full screen.
It's already in full screen.
Yeah, this is a PDF, so I cannot play with it much. Is it better?
Which other one? Okay. Which one? Yeah. That's just okay. Just a minute.
Yeah.
I did this one. It's okay. Okay. All right.
Okay.
Yeah. Thanks.
So actually, maybe I can do this. I don't know how it will work. If you have a single antenna, as I say, you have this pencil, what is called the main beam of the antenna, and the size of it, the smaller it is, the highest resolution you get. So the more details you can see on an object in the sky. So you want this to be small, but in order for the beam, for this area of the sky that you are sensitive to, in order to be small, you need a large antenna, a really large antenna, or you need to go to very high frequencies. So there are limitations to that, and a solution in order to get very, let's say, sharp images on the sky is to abandon the idea of a single antenna and work with an interferometer in which you combine the signals of different antennas. They can be spread around the world. And you combine these signals, you synchronize these signals, and you create let's say, virtual telescope that actually has the size equivalent to the distance between the elements. Okay, that is the point. I mean, you abandoned an instrument that is maybe a few tens of meters in diameter, and you jump to hundreds of meters, kilometers, thousands of kilometers, and this is what the VLBI networks are around. In order to do that, you need to know a lot about the instrument, because what you are measuring, as you have seen in other lectures, is that the front wave of the of the electromagnetic wave that is traveling around the cosmos, when it reaches the instrument, you are measuring the delay in arrival time of this wavefront in one instrument or other instruments of the interferometer. And that relates to the position of the antennas. It relates to the moment in which you are observing. It relates to how the Earth is behaving that day, and it also relates to the structure of your cosmic source. And all of these things are got together into the models that you need to clarify to get the different parts of the observation. So that is what the basic interferometer is about. Now, if we go to here, this is the concept of UV plane, UV coverage, and how by combining signals received by not only two, but many telescopes distributed all around the world, allowing the observation to last during several hours, so that the Earth rotates, the orientation of the network changes in time, and you start covering what is called this UV plane, which are sampling of the spatial frequencies. And that, as I said before, depends on a number of issues. Like we said, the source structure, it depends on the ray geometry, the atmosphere, how the wave is affected by ionosphere, troposphere, and many aspects of the instrumentation as well. So delay that is introduced by the electronics, the front ends, receivers, IFs, backends, cables. As you see, the situation can be rather complex. And at the end of the day, we have a combination of all these effects, and we need to put models. We need to put models in order to understand, well, what is it that we want to learn about? In case of astronomy, we want to learn about the structure of the source. Therefore, we need to model the atmosphere, we need to model the instrumentation, the Earth rotation, etc. If we were to, if our goal in our observation would be, for example, different, to understand the rotation of the Earth, then that would be the data we want to gather, and then we should be modeling the source structure. So the project, the concept, as we say, is very wide, and you have to focus on modeling some aspects in order to get the information from the others. If you see here on the bottom right, as the Earth rotates, the combination of these pairs of telescopes create tracks in this UV plane, and what you want to have is these tracks filled as much as possible. This is the goal of the observation, of the VLBI observation. So let's see if I can get to the next slide. Here it is. So in a nutshell, this is what we have. We have the UV coverage, therefore the measurements that we have. Each one of these points here is a pair of telescopes that are observing a given source in an instant, in a moment in time, with the characteristics of the array that is being observed. As the Earth rotates, this point becomes a track, and the different combinations of antennas create all these mesh, or mesh, I could say, that it is how the UV coverage looks like. Each pair is looking at the source, it reacts to the structure of the source, and that creates what is called the dirty image. The dirty image is the convolution of the Fourier transform of the UV coverage and the real image of the source in the sky. What we need to do is to clean this dirty image in order to obtain the real information that we are looking for. And there are lots of techniques to do that they will be explained in other lectures. But again and again, we see how important it is to have a good UV coverage, because this is the basis by Fourier transform to what is, in other things, is also called the point spread function. The point spread function is how what is our instrument? What is our instrument getting ready to observe the cosmic source? Okay. So next slide. Now the question that is a very good question is, how long is very long? we see that there are combinations of telescopes that are spread at different distances. What is it that we start calling it VLBI? What is VLBI, and what is another kind of radio interferometry that is not really very long baseline interferometry? And so not surprisingly, the reason is not very deep. Radio interferometry in all its aspects has a lot in common. I would say not very long is what we call a connected interferometer. So you can actually put a cable that will send a signal that will synchronize or help synchronize the different antennas. So possibly you are of the order of a few kilometers. Maximum, you have examples, you have ALMA, like a connected interferometer in Chile, where you have 66 antennas spread around, let's say, 16 kilometers, maximum distance between them. So you can actually put sufficient cables there to send a clock signal to all these antennas and synchronize them. So that would not be VLBI. VLBI is actually when the elements are so far away that you cannot use this anymore. So you need to put frequency standards. You need to put masers, clocks, at each one of the antennas, record the signal together with this signal of the clock. You record the signal of your cosmic source and you format it together with this clock. And that combination goes into some disk. And then you send all this data to some central facility that is a correlator. You replay these signals, this data, and you combine them, and then you create the image, okay? So this fact that you cannot connect the elements among them is a very important signal that you are doing VLBI. Then necessarily the networks have a spread. They can be regional networks. The EVN European VLBI network is called, has most of its antennas in Europe, but or the American, the US network that is all in US grounds. But you could also have global networks that spread the whole of the planet. And then you could even bring this very long baseline interferometry concept far more away, and you could have one antenna in space. This is the case of radioastron, also of VSOP. These are satellites that are radio telescopes. So they are looking at the source together with the array on the Earth. They are looking at the same source at the same time, and they are recording this data, sending it back to the correlator, and reproducing the fact that you could be observing at that time with that array. And in that case, there are, well, no limits to the distance. Actually, radioastron had a maximum distance almost to the distance of the moon, 300,000 kilometers, which would have been the equivalent size of the radio telescope if it would have been a single antenna. So the kind of high resolution that one can get is extremely high, as you can see. But as I can say, this is a summary of this first part. The VLBI, which is the highest resolution astronomical technique that exists, there is no other kind of astronomy that provides as much angular resolution as VLBI. And this is in radio, of course. But there is no fundamental difference between VLBI and regular interferometry, connected interferometry, but it's only the technology. I would say also the convenience or even a convention. And it's the fact, let's say today, still an important distinction is that the independent antenna electronics need to be calibrated, and the time of arrival needs to be set thanks to these electronic hydrogen masers, frequency standards that you have in each one of the stations. Now, with these arrays, you can achieve very high angular resolutions. For example, at the frequency of 1.4 gigahertz, 21 centimeter wavelengths, you have an array of 8,000 kilometers, like the VLBA, for example, and you can reach already a resolution of 7 milliarc seconds. And you possibly are familiar already to this kind of angular resolutions. But these kind of sizes, angular sizes, allow you to, for example, distinguish two coins that are close together on the surface on the moon as seen from the Earth. Okay, is that kind of high resolution that when applied to cosmic sources, it allows you to get very deep inside the structure of these sources. Do you have other examples here? 200 microarc seconds are got on this, let's say, Earth array at 43 gigahertz. Higher frequency means higher resolution as well, so smaller of this size. And if you go to even higher frequency, to 1 millimeter, 230 gigahertz, you can reach 30 microarc seconds, which is actually the size of the black hole, the famous image of the black hole. And that is also done with a VLBI network. So one problem that we have when we have these VLBI networks is it is true that you have this virtual telescope of a size equivalent of the distance between the elements, but the telescope is not filled with panels. It's almost, actually, all of it is full of holes. And then the collecting area, the photons that you actually get from the source, that are the actual telescopes, depend still on the size of the individual antennas. So you need both a combination of large antennas and antennas that are separated at different distances in order to create a good VLBI network. And in this sense, it is important to note that there are some antennas like the GBT 100 meters in the US, Effelsberg 100 meters, FAST in China, 500 meters antennas. Until last year, Arecibo, that you know it crashed at the end of last year, 300-meter antennas. And all these are elements of these VLBI networks to provide higher sensitivity. There is one but, a very big but, maybe for VLBI also, and it is the fact that the technique is sensitive to compact bright sources. Compact bright sources means if your source is, it has let's say, it's wide in the sky, it is not very compact, then what happens is that the interferometer will resolve it out and you will not see it, okay? So that is helped by the fact of having in your network shorter and longer baselines, antennas that are close together, sensitive to this broad structure on the sources, and also long baselines, therefore sensitive to the most compact part of the sources. Okay, so we will remember this at the time we analyze the different networks, VLBI networks. Okay, well, that was a kind of a good introduction. I will now go to the details. Well, this is how it looks, the Earth, when you just put in a map where are antennas, radio antennas that are part of any VLBI network. And you can see that there are lots of them. Of course, there are also some areas that have more antennas than others, but in general, we could say that VLBI networks are a global endeavor, and it is possibly quite accurate to say that we are able to synthesize a radio telescope as big as the whole planet. And this is the little cartoon that you can see here on the right. So, as I said, the technique started more or less when I was born. I was born in 1966, and this started 1967. I was not involved in this. But it is true that in the last 50 years, there has been a lot of developments, and this, as you see in some of these pictures, a lot of it is linked to the evolution of the technology. The first VLBI systems, they have these names, Mark 1, Mark 2, Mark 3, Mark 4. Well, not very creative, maybe. We are now in Mark 6, by the way, in the recording systems, but these early systems allowed already to format the data, save it, first in tapes, videotapes, then in discs, and nowadays you can even send the data on internet. So this is the case of the EVN, the European network, which has antennas all around the world. And all these antennas send the data by internet to the correlator, which is in the Netherlands. I will talk about it in a minute. And then the correlator gets all this data from the internet and reproduces the observation as if the stations would be connected physically at that time, and then combines the data to create the VLBI products. Okay, so so much for the history, and these are the different VLBI networks that I will be talking about. I have more or less one slide per network, a bit more in some cases, but this is to give you a glimpse of what are the different networks available, and what are the strengths or the special characteristics of each one of them. I will start with the European VLBI network, the EVN, in combination with the network in the UK, eMerlin, and JIVE, as Merlin was presenting me before. JIVE is the Joint Institute for VLBI. ERIC means an European Research Infrastructure Consortium. Don't worry, this does not go to the exam, okay? But the question is that JIVE, in the Netherlands, is the support center for the EVN. It is the center where the data comes and also the users come. And we process the data and also do the user support. This network, as I say, is the European network, but it's global. It has telescopes all around the world. Then there is the American network, the Very Long Baseline Array, the VLBA. There is the Southern Hemisphere, mostly in Australia, Long Baseline Array, LBA. The East Asian VLBI networks, that is a combination of the Japanese, the Chinese, and the Korean networks. Then the being deployed African VLBI network, the AVN, which I'm extremely fond of. And I will close this centimeter wave with networks with the case of Radio Astra, the space telescope. So the European VLBI network, okay? There are 22 radio telescopes. They are distributed all around the world. You have seen the map just a second ago. These are the frequencies of operation. So it is quite wide frequency between 1.4 gigahertz and 45 gigahertz. That allows to do a lot of science cases. It has only, however, limited frequency flexibility. And this is an issue that will be very important. So the network can operate typically at one of the frequencies at every time. It cannot observe simultaneously at several frequencies. There are other networks that can, okay? So we will highlight that when the time comes. It is quite sensitive because it has big dishes. We mentioned before the Effensberg 100 meter, also Sardinia 64 meter. Gieves in Spain is a 40 meter telescope, so big dishes, and it can work at 4 gigabit per second, which means that it is quite sensitive in sampling the data and sending it to JIVE. It can also work in real time. This is when I meant that the data can be sent on internet. Well, that means that the data is taken by the telescope and is sent immediately in real time to the correlator. And this is the only network in the world that has this capability, the EVN. You can also send the data, what is called electronic transfer. You send the data on internet, but it's not processed in real time. This is another feature. But what we mean here is observing and getting the data and processing the data at the same time, in real time. So the EVN works in 3 sessions per year. So it's not a dedicated instrument. It means that the telescopes have their own programs. They belong to different institutions, but they get together to run as a network 3 times per year. And during that time—
Sorry, Paco.
Yes? Yes?
We lost power for, I think, about 5 minutes. So if you could go back a bit. Yeah, when you're talking about the correlators, that's where power went out.
Oh, that's interesting. Well, you're back. It's more interesting even that you're back. Okay. So, okay, no problem. I can go back. Let me see. We were talking about the different, what was it?
Yeah.
Here, right? Okay.
Yeah.
Well, this was only the let's say, historic description on how the technique has evolved, and it has evolved together with the technology. Okay. So the first VLBI, which started more than 50 years ago, got the data from the telescopes, and that was recorded into videotapes. The technology evolved, and later You could record the data on hard drives, like it happens today. But more recently, you can even send the data on internet. And you can, when you do this, when you send the data on internet, you have, well, the case here feature is the EVN, the European VLBI Network, with all these telescopes distributed all around the world. They can send the data to the correlator, to the processing center, which is JIVE, which is where I work in the Netherlands. And this can be sent, as I will explain later, in real time, or it can be sent just to avoid the transport. Let's say to put the disks in a truck, in a plane, and send it, and possibly receiving it several weeks after the observation. When you do this by internet, all these times are much speed. Okay. So okay. And then I started explaining the different centimeter VLBI networks, that there are a number of them. You could call them, they could be called regional networks, but actually many of them are global. They have telescopes all around the world. The European VLBI network has telescopes in South Africa, in China, in America, in Korea. The VLBA, the Very Long Baseline Array, is mostly a US instrument. The Long Baseline Array is mostly in Australia, but it also collaborates with a telescope in South Africa. Then the East Asian VLBI network, which combines the networks of China, Japan, and Korea. The African VLBI network, which is being deployed. There is already one antenna of the AVN in Ghana. And just to finish this list, the Radio Astron project, that is the space satellite. Okay. So, and then I start, yes, here it is. Then I start with the AVN, okay? So the AVN, the European VLBI network, let's go to the map. I think it's more easy to see. As you see, most of the antennas, up to 22 antennas, are located in Europe, but there is also an antenna in South Africa. There are 3 antennas. The antennas of the Korean network are collaborating with EVN, and until very recently, there was one antenna in Arecibo, in Puerto Rico, that collapsed at the end of last year. Many of these antennas are very large. We said before how important it is that in order to have a sensitive VLBI network, it's not the fact only that the telescopes are far away or at different distances, but also that the individual telescopes have to be big, because that is what provides the sensitivity to the whole network. So we have Effelsberg in Germany, 100 meters. We have Jodrell Bank in the UK, 76 meters. Sardinia in Italy, 64 meters. Jeves in Spain is 40 meters. The Tiam antenna in China is 65 meters. So you see all of them are really big parabolic antennas. And as I was saying before, what they do is that they operate, they are instruments that have their own programs. They depend on different institutions, but they 3 times per year, they get together and they create the EVN. They, for 3 weeks every time, 3 times a year, they cooperate, they coordinate, and they have the same observing program, which is essential for a VLBI network. They have to be observing the same source in the sky, all of them at the same time. What they do is then they collect this data and send it to a processing facility that for the EVN, it is JIVE. And JIVE is, as we said here, the Joint Institute for VLBI, Eric, that is what JIVE means. And it is the processing center and the coordination center for the EVN located in the Netherlands, in a little town called Dwingelo. So that's where I work. What we do at JIVE is we collect the data and we also provide the user support to the EVN, to the users of the EVN. Some characteristics of this European VLBI network are the operating frequencies, and we will be looking at these characteristics at different networks so we can compare. So the EVN works from 1.4 gigahertz to 45 gigahertz, not continuously, okay, in several bands. And this is an issue that is important when we talk about frequency flexibility of the VLBI network, since the network can maybe only observe one of these lines per at a time. And if you need to move to another line, you need to retune the network. Okay. If there is any problem with the connection, please let me know. Okay, so I continue. For the sensitivity of the array, it's very important how much data it can collect. In this case, it is 4 gigabits per second per telescope. 4 gigabits is a lot of data. 4 gigabits per second per telescope. So you can imagine how much data is crossing the world and how much for the EVN is going into Jive. That is another of the aspects that makes this instrument so sensitive. Actually, the EVN is the most sensitive VLBI networks in the world at some frequencies, and this because of the combination of this very high data rate recording and also the size of the telescopes that we just mentioned. And what makes the EVN very special as well is that it is still, for the moment, the only network in the world that can operate in real time. So you can observe the source with your network, send the data by internet to Jive in the Netherlands, and process the data and get your image in real time, instead of recording the data, shipping it, and then several weeks later processing it. And that has very nice applications for the EVN. The EVN has an open sky policy, and this means that any astronomer in the world can use the EVN, and the proposals are only evaluated on scientific merit. There's no quota per country or anything. And if your idea is good, you can use the EVN. And as I said, the Joint Institute for VLBI, JIVE, correlates the data and provides the support to the users. There is a website there that you can look at. We have gone through this. There is a newsletter of the EVN that is published 3 times a year. That is also in the website. You can look at it. And just to close the loop here, the proposals that are sent to the EVN have to be observed in the sessions, in one of these 3 sessions per year. And the data, once it's taken, is available to the users for 1 year in a proprietary mode. So only the team who proposes the observation has access to this data for 1 year. And after that, all the data becomes public and anybody can use it. Okay? All right, so for Jive, this is a bit of the same. So you have this for reference later if you want to get through the slides again. This is a consortium of countries. There are 7 countries at the moment that are partners in Jive. The Netherlands, which is the host, France, Spain, the UK, Sweden, Latvia, and Italy. And there are agreements with other 3 institutions in South Africa, in Germany, and in China. And the rest, I think we've gone through. That is the support of the EVN and the research development support to the users. Okay. Very important is the user support. This is essential because it is understood that the astronomer, you as astronomers, will like to be solving problems, astrophysical problems. You don't want to be necessarily the expert and the master of each one of the possible techniques that your problem will need to combine. So VLBI is a technique that requires, well, a lot of expertise to work on, and this is why Jive has experts ready to help the users, so to avoid that the EVN users need to become also VLBI experts. So there are lots of schools, training exercises, and this is one. This is one. We have been participating often with the data and other projects like Jumping Jive from the EC, which help promote this kind of training. Very important, the EVN, very luckily, in recent times, works together with this other instrument, Merlin. Merlin is the multi-element radio link interferometer. This is it is a connected, especially connected interferometer because it's connected not by cables, but by radios, at least in its inception, in this concept. And this is in the UK. These are 7 antennas, including the big dish in Jodrell Bank, the Lovell 76 meter. And they are spread around 217 kilometers. And the very important thing that this instrument, first of all, it's an instrument on its own. Merlin, or now eMerlin, extended Merlin, is an instrument, a fantastic instrument on its own. But when it is also integrated and combined with the EVN, it provides the short baselines, which the global networks often have very difficult to provide. So if you want to get all the scales in the structure of a source, you want to have all kinds of baseline, shorts and long, and the combination of eMerlin with the EVN is a fantastic instrument. This is how it looks when you think of UV coverage. We said before, you want to cover this with tracks as much as possible. Usually what happens is that you have holes. You have an antenna packed together and another one very far away. You will have a track that is very far from the others. In this case, you see that the combination of eMerlin with the EVN provides a fantastic UV coverage. It's really very, very nice instrument. Okay, so far, so good for the EVN. This is the very long baseline array in the USA, 10 antennas. Well, this was designed as an instrument for VLBI. So one of the things that you see immediately is that all the antennas are equal. They are the same construction, and which is not the case in the EVN. All the antennas actually in the EVN are different. And that creates some trouble sometimes. So once you have 10 identical antennas, you save a lot of effort in putting the instrument together. It also has another very important feature, and is that it has continuous operation 24/7, not like the sessions that happen with the EVN. Okay. It also has a very wide frequency range of operation, 1.2 to 92 gigahertz. And it can record, just like the EVN, up to 4 gigabit per second. When you see that some of these characteristics resemble those of the EVN, you can immediately think that why don't these networks could work together? Because they have a lot of things in common, and actually they do. They work together and they create a global array in which the EVN and the VLBI can be coordinated. Can you confirm that the students are there still? I don't see the video anymore.
Yeah, we're still here.
Okay, fantastic. Thank you. Okay, so that is the importance of the VLBA, as we said, compared to the EVN, is that this instrument is on the sky all the time. The EVN is only 3 times a year. And also, at the time you get your program approved, the VLBA has a system called dynamical schedule, in which most of the time is optimized by putting the different projects at the moment in which the conditions of the array and the conditions of the sky, etc., maybe the weather even, are more favorable to your project. And that is not so much happening in other networks. So in that sense, the VLBA is a very, in many senses, a very advanced VLBI network. The VLBA joins with some other few very sensitive telescopes, very big dishes, to create what is called the high sensitivity array, the HSA. This is the VLBA together with this VLA, the very large array, which is in the US, in New Mexico. This is 27 antennas of 25 meters. You see the picture there. They can be phased up and act as a one single instrument in the VLBI network, but with a huge sensitivity. You combine that with a 100-meter green band telescope, with a 100-meter Effelsberg telescope in Germany, until recently with the Arecibo 300-meter telescope. And you can imagine that network was extremely sensitive. Well, one of the features is that it only operates a few hours a year, which means that, well, you really have to justify very well that your program, your science, needs this high sensitivity in order to be able to use the instrument. But the instrument exists, okay? Now, we go to the other part of the world, and we talk about the Southern Hemisphere Long Baseline Array. It's called the LBA. This includes all these telescopes that you see in Australia, Parkes telescope, 76 meter, the Australian Compact Array, ATCA, the MOPRA array as well, and also other antennas in Tasmania, like Hobart. And then that is the regional VLBI network in Australia, but it combines with the telescope in South Africa, the same that is a member of the EVN, by the way, the Hartebes-Stoke antenna, and it creates this Southern Hemisphere Long Baseline Array. Again, you will see that the frequencies of operation are quite similar to the others, which creates all this concept of working together. And of course, this network, the LBA, is especially useful when you are looking at cosmic sources that have very low, very south declination. Therefore, they are not visible to antennas in the northern hemisphere. You have the website there in case you want to see a bit more about LBA. Now, I'm moving into the Asian networks. As I said, there are three, the Japanese, Korean, and Chinese, that they combine together to create the East Asian VLBI networks. This is the specific case of the Japanese instrument that is called VERA, VLBI Exploration of Radioastrometry, and this was built as 4 antennas for complex in different islands of Japan. All of them are the same antennas, and they are built for astrometry purposes. And when you do VLBI, often in the processing, one of the things that you realize is that when you are able to calibrate your data and get very sharp, very detailed images on the cosmic sources, often what happens is that you lose the position of the sources. You don't know where the source is because you have to refer it to something. Usually we refer our source of interest to some nearby quasar to which we have very accurate positions. This instrument is built already to observe both the source and the quasar at the same time. Therefore, it has what is called a dual beam capability. There are 2 receivers per antenna pointing at a slightly different positions in the sky, up to almost 3 degrees in the sky. You can there observe a number of quasars and your source of interest at the same time, and you can easily solve this problem of the absolute positioning. And once you have absolute positioning, you can do astrometry. And that is why this instrument has been used extensively for astrometric studies, for example, of our Milky Way. This also operates at a slightly higher bandwidth, frequencies that the AVN. For example, you see here K and Q band. Q band is 43 gigahertz, K is 22. And sometimes it combines with other antennas in Japan to add more sensitivity, like this 45 meters. The antennas of VERA are of 20 meters. There are 4 of them. So the VERA instrument is the Japanese case. The Korean case is called the Korean VLBI Network. They are here in Korea. There are 3 antennas, 21 meters. They're very modern antennas. The distance is moderate. It's about 500 kilometers in total for the 3 antennas. It is an associate member of the AVN. This is why I put this map here. But what makes this network especially interesting is it is the first that allows to observe simultaneously, because they have 4 receivers in the focus at the same time, and they can observe simultaneously at 22, 43, 86, and 129 gigahertz. And that has a lot of applications. And as I say, this concept is so important that it is being implemented in other networks. The way this works in the KVN is by a kind of complex technological array on an optical table where all these all these receivers are located. And now they have developed a concept of a very compact receiver. This is what this picture is about, in which all these different frequencies are into one single cryostat, and that can be then easily implemented in the other networks like the EVN, who are considering to implement this receiver to increase the frequency flexibility. Okay, the 2 KVN and VERA often work together, and they create this network called CAVA. CAVA has been operational since 2010. And it mostly works at 22 and 43 gigahertz, as you see here. They offer 500 hours per year. So again, these networks, these combinations of antennas are operational only sometimes during the year. These are not like the VLBA that are on the sky all the time. And in this case, CAVA combines both the multi-frequency possibilities of KVN with the dual beam capabilities of Vera. Okay. When the Kava or KVN, Vera, and also the Chinese antennas, some of them members of the EVN, combined together, they create this network called the East Asian VLBI Network. This is a huge network. This operates 22 radio telescopes in these 3 countries. Again, at frequencies quite compatible with the other networks, especially 22 and 43 gigahertz, and also in sessions. These numbers may be updated. If somebody listens to this talk some years from now, possibly this will not be 500 hours anymore, but they have this concept of a session, like the same that the EVN does. And this is a very active, very wide and very active community in Asia, organizing what are called the EAVN scientific workshops every year, that the same that other networks like the EVN do, is a very good opportunity to learn and to know what is going on, and also, of course, to present the results of the studies that have been done with these networks. So you can see here that the network in East Asia is very complete with lots of telescopes. One of them fast 500 meters, so also very sensitive. It does not work in real time like the EVN. Okay, so different networks have different characteristics, as I said, but this is also very much to take into account. Okay? I have here 3 slides with a table of comparison. I'm not going to read them, okay, but just have them there for future reference. What are the access mechanism, proposal types, what are the deadlines for applications, how long the projects can be scheduled, what are the observing cycles, how does the scheduling works, and how long is the proprietary period of the data for the EVN, for the EAVN, for the VLBA, for the LBA. All these major, as I said, centimeter wave VLBI networks. Okay. And now we come to the AVN. The AVN is the African VLBI network. Its concept starts on the deployment of radio astronomy in Africa. For that, Dara has been a huge, fantastic ambassador. This is development in Africa by radio astronomy. Okay, it is understood that in Africa, in many African countries, just like in many countries around the world, it's not only in Africa, there are unused communication complex that years ago were working for communications. They were satellite communication for these countries. They have huge antennas of 32 meters, but they are not used anymore. And the concept of refurbishing these antennas so that they can be used for radio astronomy, as radio telescopes. The concept is very interesting, and as I said, this is to be applied in Africa. The first case is Ghana, the Ghana antenna, who was refurbished successfully and was able to join the VLBI observations already in 2017. This is the first in the AVN. Of course, the telescopes in South Africa as well. But then you see all these little dots here that are the locations of all these other telescopes that wait to be refurbished. I think the point of refurbishing is it's an attractor. It's an attractor of all who may be interested in developing radio astronomy in a country, because you have a telescope there and you have an antenna, and you can get together the scientists with the universities, with the companies who want to refurbish the antenna, with the technology centers, with international partners, and all of them focus in this project, therefore making it extremely attractive. And Ghana was an example of that. How the EVN will evolve, there are other options, and the options of installing maybe a more modern antenna in these sites of the kind of the SKA, which is being built as we speak. So maybe there are other options, but I still think that the concept of the refurbishing of antenna is especially attractive precisely because of this attraction power of all parties involved, who can work together for many years and not just, well, just get a telescope, let's say, with the key in your hand, but then maybe you haven't created a community yet to use it. So in that sense, Jive has been quite active and collaborating with data, and you have here some of the examples. The last of this list is RadioAstron, the space telescope. It ceased of operations in 2019. So actually, during 8 years, we had a 10-meter antenna orbiting the Earth at distances up to 300,000 kilometers. The results of the mission were very unique, even if the imaging capability was kind of limited, because of course, at these long distances, you almost have one single baseline. Okay, all the Earth to satellite baselines, all these combinations are more or less equivalent. They are more or less the same. But still, it was a really nice project, and we already think that we need another space telescope because there is a lot of science still to do. Okay, to wrap up on these networks, I like to mention these others. They are at different frequencies that the ones I mentioned now. The GMVA Event Horizon Telescope are high frequencies. The International LOFAR Telescope is low frequencies. And then I would like to have one slide on the SKA and the geodesy counterpart of VLBI. This is the global millimeter VLBI array, the GMVA. This is a global network, as you see, but it is focused on one single frequency, which is 86 gigahertz, 3 millimeter wavelength. It observes twice per year, only for a few days, 3-5 days per day, each time. But it is open skies. I mean, anybody who wants to get super super angular resolution can make use of this very high frequency network that can provide 45 microseconds in the sky, which is already very, it's quite a lot. Also very sensitive. Okay, so this is the global millimeter VLBI array. You have there the link as well. This is a very famous, the Event Horizon Telescope. Well, this is not really a telescope. Actually, it's a project that is built on top of existing telescopes. These telescopes get together, as you see there, usually one time per year. And they are very focused because they are a project in the observation of shadows of black holes, or let's say, in particular, the inner regions in galaxies where there are black holes. So you can see images like the one you see here, a world famous image of the black hole in the center of AM87, but also the jets that are coming from these central engines of galaxies that you can actually deep into the very inner part of these jets and understand how they are generated. So this instrument continues providing data, and we are now expecting, of course, everybody, the results on the center of our galaxy, Sagittarius A star, which hopefully will come in the near future. This is the Event Horizon Telescope. In the other area of the spectrum, because the Event Horizon Telescope, as you see there, operates at up to 345 gigahertz, is really very high frequency. At the other end of the spectrum, you have LOFAR, or the ILT. The ILT is a long, well, the LOFAR means the low frequency array. So this low frequency operates at megahertz, not at gigahertz, or not even at 300 gigahertz. But as you see, it's also a VLBI network. Most of the elements of LOFAR are in the Netherlands, but it also has these international stations that spread a lot of Europe, and it is therefore on VLBI techniques, which applications to astronomy, to geosciences, and other issues, even agriculture, space weather, with lots of synergies with EVN. Why do I say this? Because it happens often that the same observatory which has an EVN antenna also has a LOFAR antenna on the same ground. So in that sense, it is possible to talk to each other and to exploit these synergies for ILT. In midway between one and the other is the SKA. The SKA is the next generation VLBI instrument. As you know, it is being built. The low frequency part in Australia, in the desert, the Western Australia, and the mid, called, or high frequency part in South Africa, to be extended in the future to most of Africa. So this SKA, the first phase, SKA1, which is 10% of the full SKA, is centered on South Africa, is the one that is being built today. And it can be complemented with the long baselines of the other VLBI networks. Therefore, we are developing this concept called the SKA VLBI. SKA VLBI means integrating the SKA into a VLBI network. That could be the EVN, or for the Australian case, it could be other antennas, but of course at that frequency range. There is a lot of work done towards the SKA, and in particular the pathfinders. Therefore, we have in South Africa MERCAT. MERCAT is 64 antennas that are already operational, a beautiful instrument that will be the core of the SKA1 mid that is going to be built in the next 10 years. So there are already VLBI tests with MERCAT successful, and we think that this is the right way to go to actually make SKA VLBI a reality in the future. There is, this is almost my last slide, a complementarity. Why do we need all these instruments? Well, they are complementary. The frequencies that the different arrays are sensitive to, their other characteristics, whether they have or not frequency flexibility, whether they are regional or global, whether they are on the sky all the time or only some sessions per year. All these things are complementary. So you have here, for example, just a picture of what is the frequency coverage and angular resolution, and you see that the SKA covers, well, let's say the broader scales in the sky, while when you go to the global VLBI networks, you start to get to pinpoint the very fine details of the object. So you possibly have to observe your object with several of these configurations to get the whole picture. And last but not least, I said at the beginning that if you have an array of telescopes looking at the sky, you have a problem that you have to solve. Okay, you can model a number of things to get the information on the rest. Now, if your array, your network is an astronomical, purpose-driven, science-driven instrument, you will like to measure the positions of your antennas, you model the atmosphere, model the electronics, so that anything that is left is due to the structure of the source. That is actually what you want to discover. But this network I'm presenting to you today now is the International VLBI Service for Geodesy and Astrometry. What it actually does is reverse the problem. It uses sources in the sky that we know how they look like. We usually uses very distant quasars that are point-like. They don't show, in principle, any structure. And therefore, you don't focus on that side of the problem, because your side of the problem you want to focus is the behavior of the Earth. Therefore, you will measure with high precision the position of each one of these antennas, and you will monitor the movement of the changes in that position, because it's related to tectonic plate motion, is related to Earth orientation, for example, position of the pole, duration of the day, and these are the kind of parameters that this kind of VLBI network is going to be interested on. And this is the way in which the reference frames are built. This is a very interesting use of VLBI. Often observatories that are VLBI observatories do both astronomy and also geodesy, even if You need some special characteristics nowadays for the geodetic networks. I will not get into that today, but it is true that these products that come from the IDS, from this VLBI service for geodesy, are really unique and essential, a unique contribution of VLBI in the area of geodesy. So I will leave the message today, as you have seen, that there are many VLBI networks. Each one has their own characteristics. They complement each other, but there are also many things in common. And this concept of a VLBI, global VLBI alliance, has been set precisely to strengthen the synergies between the networks, so that the different networks will have their own program, can also talk to each other, and can also exploit both the and ensure the technical, let's say, compatibility, but also exploit complementarities between them, therefore giving to the users the best possible scenario of instrumentation of research infrastructures. You can track the evolution of Global VLBI Alliance in these web links. So thank you very much for today. And I'm here open to questions or some comments. I also have some little exercise if you want to think a little bit about it now or on Slack. And last but not least, remember, there are lots of events that are happening, scientific conferences, technology meetings, schools like this one that are organized by all these networks, and that you have the opportunity to join. Thank you.
Thank you so much, Mervin. You want to take off from here?
Well, I think you're in the room, Alex. So do you want to see if there are any questions and people can come up and ask them?
Okay. Any questions?
I don't know if you can put the room camera back on. We've gone to the rainbow stripes.
Camera. Yeah. Is it on? Is the
I see the group.
Yeah. Yeah. Thank you.
Hello, Paco.
Yes. Hello.
I wanted to find out with regards to the AVN network. Apart from Ghana, how far have the other African countries that are connected to it, how far have they gone?
Yes, that is a very difficult question to answer, okay? Because there is a variety of situations. I think, as I said, the concept is still there. The concept of refurbishing a communication antenna is being exploited because we see that it is very useful. Actually, it is exploited not only in Africa, but also in Latin America. There is already a group of people in different countries in Latin America that have exactly the same situation. And, 32-meter antennas not being used anymore. And they heard of the AVN and they said, and they heard through data, of course, and they thought, oh, this is a good business for us. But this is not necessarily an easy thing to do. Okay, the example of Ghana has demonstrated that there is a lot of work to do. Possibly the Ghana case being almost the first one was a bit exaggerated, and maybe the next cases will not be so, let's say, complicated in that sense. But in any case, there is the option for each one of the teams and the countries to study different alternatives. In my opinion, my preference would still be refurbishing, but it is also true that it is possible to purchase an antenna, a more modern antenna that possibly gives the same or even better sensitivity and easier other aspects like well, operational aspects, better frequencies installed in the system that these special beam guide antennas allow, etc. Right? So I would say that the rest of the countries in the specifics of refurbishing antennas are not going as fast as we would have liked. Okay, and I think there is still a time to engage in one or the other models of going forward with refurbishing with some aspects that I think are beneficial, or going to abandon the idea of refurbishing and then going more to the idea of getting a new antenna on the ground. But in any case, in any of both cases, the training is essential and has to come earlier. You cannot start training the people when the antenna arrives. You have to do that before. Therefore, these kind of events are very timely everywhere.
Any more questions? Any more questions? Okay, so there's one more question coming up.
Yes.
Yeah. Now, my question is about the arrays. We have a lot of antennas, and what is the minimum distance between the antennas? Because we are looking for signals. If they are too close, we might not get the right signal. So what is the minimum distance between the antennas in the array?
What you mean, Eric? Which is the instrument that you are referring to?
Array.
I think any array, I think.
Yeah.
Any array. Okay, thank you. Yes, it is. I think this is a very good question because it always bothers us that sometimes you cannot choose where the antennas are. Okay, you just take the antennas where they are, and it is often that the antennas end up being too far away. It is therefore useful to complement the faraway antennas in different countries with antennas that are more close together. How close you could put them? Well, I mean, you can put them all as close as they can also almost touch themselves, okay? There are examples in connected interferometers like the VLA or ALMA, in which the minimum distance can be almost the diameter of the antenna, okay? Now, I don't know why you would do that, okay? The question, of course, is that it has to be fitted to your science project. If you want to observe some structures in the cosmos that are very wide, very big, you need to adapt your array to be sensitive to those sizes. And that means antennas that are closer together than if your object in the sky is very compact. But at the end of the day, you want to combine everything. You want to have antennas that are close and far away because you want to be sensitive to all possible structures in the sky, the compact ones and the non-compact ones. Okay. I don't know if that answers your question.
Yes. Oh, he says yes.
Thank you. But as I said before, when you mean VLBI, is that the antennas are separated so much that you cannot connect them with a cable, and you cannot send the clock signal. This typically today is of the order of 100 kilometers. I mean, you could synchronize two antennas that are of an order of 100 kilometers distance, but if you go longer than that, you need independent clocks, and then is VLBI. Okay.
Right.
I actually have some questions for you. If you don't have questions for me.
I'm just conscious of the time, Paco, and how we handle that.
Then we will put them in the Slack.
Yeah. Do you have them like in a document that we can post, or?
Yes, no problem. Well, it's like an exercise of what kind of network do you think is best for this or that.
Okay, that sounds really good.
Okay.
But I think, well, if you email them to me and Rob, we can put them on the website then.
Absolutely.
And then they can have a go at them, and if they've got any questions, they can ask in Slack. I think it's probably the way to go there. I don't know if there's any more questions from the floor.
Yeah, they said the floor is swept. No, no more questions.
There's a lot of information in this talk. I apologize.
It's been a lot of information this afternoon, I think.
Yes. Well, you have it there. You have the slides. Okay.
No, that's really good, Paco. So thanks ever so much for doing that. That's really good.
Thank you, everybody, and good luck with the school. I think this, as I say, this opportunity is really great.
Yeah.
Take care.
Thanks, Paco.
Okay.
Thank you.
The battery died. Okay, so I take over from here.
Well, Alex, I don't know if you saw my message, but I had a suggestion since we're already past 5 o'clock there, right? Yeah.
Okay, I have not seen it yet. Let me
Well,
check.
I don't know if you want to. There's more changes coming to the timetable because we're going to have a live Pulsar demo tomorrow afternoon now.
Tomorrow.
Yeah.
Okay.
So I've already moved Tio's short talk to Friday afternoon instead. So one option would be to move your talk to Friday afternoon as well, rather than now, if the students are tired. Nope. You've already had a lot of talks this afternoon.
Yeah, that's okay.
Does that make sense?
Yeah. It does make sense.
I mean, it's up to you. You know, you can gauge the situation better than I can. So.
No, I think they are tired already.
I got that. I mean, you had a late night last night, so
yeah.
From everything I understand, you had a good night observing last night. So that sounds excellent. That you actually got that experience with the big telescope.
Yeah. So.
But I hope the students enjoyed that experience. So.
I think they did. Some even wanted to observe the moon.
Yeah, well, that's probably less interesting at the radio telescope.
That was around 5 a.m. there, about when the moon was setting. So.
Yeah, no, it sounds really good. And looking at the data that Proven showed me earlier, the data looks nice as well. So, so now that we've agreed that change as well, I'll send everyone around a new revised timetable. So Tom Scragg will come back tomorrow afternoon and you can actually see the Pulsar backend in real action in real time, and so hopefully that will round off the everything to do with the big dish. So that'd be good.
All right.
Okay.
Great. Yeah.
I'll stop this. I'll stop the Zoom now and wish you a good evening.
All right. See you tomorrow.
See you.